The final iterative method we'll consider in this chapter of solving linear system is called the conjugate gradient method. This method is very sophisticated and has really nice convergence properties, a little bit more superior to Gauss-Seidel. And what I'm interested in you following is the construction of the method. I'm not asking you to memorize this development of the method, but to try to follow how it was created. Because the construction is very innovative in ways of exploiting the structure of the matrix and finding ways to take a guess at the solution and very effectively update so that you really you can almost guarantee convergence and accelerate it. So this plays upon vector calculus, which you had in third semester calculus. And the idea is that we look at a particular problem based on a function of a vector. In this case, the function is called f of x, as you see here on the slide. But the x here really is multidimensional. It lives in Rn, n-dimensional space. N could be 2, 3, 4, 5, whatever, but it's definitely not it's not the real line. We've moved beyond the real line, so we're in multidimensional space. And so this is a vector-valued function right here. So what you have here is a vector-valued function where x is the vector, and we've described it using matrices as well as vectors. So it's 1/2 x transpose ax minus b transpose x. So as you can think about what you would obtain from this kind of form. You actually will map the vector x to a particular scalar, because 1/2 times, first of all, x transpose ax is going to give you a scalar value. B transpose x is an inner product. That's going to give you scalar. So this function is basically mapping. So if we wanted to write just some understanding of the range and the domain of the range, it's mapping Rn. It's taking a vector and mapping it to R. So it's mapping it to the real line. Now, a very important two important properties for the matrix A defining this particular vector-valued function f is that A is symmetric, positive, definite matrix, and certainly, as we said before, x and b are vectors in Rn. So the fact that the matrix is positive, definite is crucial. Symmetry as well, but especially symmetric and positive, definite. Because you'll remember that one of the definitions of positive, definite is that this particular form x transpose ax will be strictly positive regardless of what x. Assuming that x vector is not 0, where all the components of the vector are 0, right? That'll be a strictly positive value. That's very important for this construction. Now, remember, if you were on the real line and f of x is a function of x and x lives on the real line, then the minimum of a function, just from first semester calculus, you get the min or the max by computing the derivative and set it equal to 0 and figure out where that x is. That's usually called a critical point or a critical value for the function. But x now is a vector. It lives in Rn, so it has many dimensions, x1, x2, x3, say up through xn. So it doesn't make sense to talk about a derivative in any one dimension. You have to think of sort of the derivative across all the dimensions. That's called a gradient, and you may remember this notation as indicated over here. It turns out the gradient for that particular function f, as we've defined it above, is actually ax minus b. So just like you did in first semester to find those critical points, if you set the gradient equal to 0 here, notice setting this gradient, which is actually ax minus b, if you set it equal to 0, then that says that ax would have to be equivalent to b. So what's interesting about the conjugate gradient method is that in the minimization of this vector-valued function f, you'll find the minimum when x actually solves the linear system ax equals b. How cool is that? So if x solves the linear system ax equals b, it's also minimizing that vector-valued function in Rn. And that's the interesting parallel going on in this method. Yes, we are solving a linear system. Absolutely, that is the goal. But in the process, we're minimizing this function, and how we get to that minimum will actually get us to the linear solution of ax equals b. So what we want is we wanted an iterative form like we've had before, but the particular iterative form we want now looks like this. That will, if we took a guess xk and we wanted to produce a new guess xk plus 1, we want the current guess to be a linear combination with a search vector, sk, and then this alpha k, which is called the step length. So alpha k is a scalar. It's a real number. And sk is some other vector. So we're trying to get closer to the solution through this space by using a search direction, hopefully to get us towards closer and closer to that minimum of the function f. When we hit the minimum of the function of f, we've actually solved the linear system, because that's where the gradient would be 0. So if we found an update xk plus 1, we want to see how well it minimizes the function f. If we wanted to minimize, if we wanted it to be the minimum of the function, then we'd want to choose the alpha k in a way so that a times our guess, xk plus alpha k sk is equal to b. Question is why? Well, we just said that the minimum for the function occurs when you solve the linear system. So if our update of xk plus alpha k sk solves the linear system, then we know we minimize the function. So that's that parallel logic there. So let's suppose we define the difference between a times xk and b, or in this case b minus xk, equal to rk. Now, if rk is equal to 0, we're done, right? Because then xk would solve the linear system, and in fact, it would also minimize the function f, as we defined earlier. But we're going to call it the kth residual vector. And again, we're hoping that axk plus alpha k sk, that this quantity is equal to b. If you did some algebra, just some very multiply through by a, collect the terms, then what you would have is alpha k times ask is equal to b minus axk, and by definition that's equal to rk, because that's what we're calling the residual, all right? So if we do if you solved that for alpha k, you could show that this would be a representation of what that step length needed to be. If you're going to assume that this update is going to minimize the function, right? So this, just by using this idea of the gradient being set at equals 0 to achieve a minimum for a multi-dimensional function in Rn, we now know how to choose the step length. And again, this sk transpose rk, that's a scalar. Sk transpose ask, that's a scalar. We also know something very special. We know that sk transpose ask has to be greater than 0. Why? Because we assumed that the matrix was symmetric, positive, definite. Okay. That's crucial for the conjugate gradient method. If the matrix failed to be symmetric, positive, definite, the method could break down in the sense that you could get to a point and never really get to the minimum, get sort of stuck in a black hole, so to speak, and trying to optimize and trying to get closer to the minimum. It could break down. So the remaining question is, all right, so that tells us how we would get the alpha k for our update. How do we choose the sk, the search directions, so that, again, we would minimize the function f? Well, one way to choose the search direction sk would be the negative gradient of the function. And again, remember, for this particular function f, we said that the gradient is ax minus b, which now we have defined as the residual. So after k steps, this kth search direction could be just the residual rk. It's the direction of largest negative change in f. This particular approach actually has a name. If you choose the search direction that way as your kth residual, That's called the method of steepest descent. That just means you would see how well you solve a solution. You would take your xk plus 1, multiply it by a, subtract b, that would be your residual, and then use that as the next search direction. If you ask the question, well, how well does that work? It tends to converge very slowly. So it's very, very slow. So steepest descent is a fairly reliable method, but it's just too slow. It takes way too many iterations for a very large scale problem. If we're solving, hundreds of thousands or a million unknowns, it'd be way too slow. So the alternative approach, which is associated with conjugate gradient, is to make the gradient conjugate with the search direction. In this case, you want to choose the sk plus 1 indicated here as a form of the k plus first residual that you would obtain plus a linear combination of a search direction sk in another step length called beta k. All right? And the idea is that you would choose successive SKs here so they are conjugate. Conjugate in this case means SK transpose A SK equals 0. I'll show you a picture in a minute that really explains what this means. But effectively what it means is you don't do any backtracking. That as you are minimizing and you're using search directions, you're using, you are minimizing in each search the most effective way without any backtracking over any other search direction that you've done. Okay, so it doesn't waste time. It becomes very efficient that you use all the search directions independently in the sense of they're almost perpendicular, you could almost think, to each other, so that there is no backtracking and it's the most optimal way to zero in on the minimum of the function. So our search directions have a form where you update the residual. If you just use the residual, that's steepest descent. But we're trying to improve upon steepest descent by making our search directions conjugate. Hence the name conjugate gradient. So again, the advantage of conjugate gradient is that it preserves the minimizations that you've already gotten. You are making the function f, every step it's achieving a smaller value. In other words, you could imagine that, as we iterate and go along, the value of f is dropping as a scalar, as opposed to either becoming stationary or even oscillating like this. We don't want to see that kind of thing. Every step, the function is getting smaller and smaller. Okay. So one pictorial way is if this diagram here represents contours for f. Remember what f does. It maps Rn to R. So we're trying to see where it ends up every time. And let's suppose that the minimum is achieved right there. That's the solution in multidimensional space we're getting. And let's just suppose we're representing our initial guess, out here. And of course, in Rn, that's a vector, right? It gets, but f of that will be mapped to a particular real value. So what could happen is that we, let's say we start a particular vector, then we do an iteration and we end up here. What can happen with steepest descent is that, you might, sorry, don't mean to make a comment. You might end up moving towards the similar direction again. So we'll just say, suppose it started here. It might move up in this direction, but it could turn around and move back. It could go back and forth in this sort of approach, eventually getting to the solution. But this is what we mean by backtracking. It's obviously not learned that, it's achieving the same value again and again and again, so it's not minimizing directly every step, getting closer and closer. What we really want to do is zero in. We'd like to just try to move down the hill. If this is the bottom of the hill and this is the top of the hill, the steepest descent could be going back and forth the valley, basically, until it finally does get down to the minimum value. So I'm going to select this and then take it out. Conjugate gradient, the idea here is that with an initial guess, it would actually, maybe take a step here and achieve this minimization, and then it'll be orthogonal, go up here, and then perhaps go here, and then directly in. I mean, I exaggerated there, but the idea would be that because these are conjugate directions, in other words, there's no backtracking at all. You went one direction and then orthogonal another direction, and you zeroed in, hopefully faster, to the solution. So again, this idea of conjugate directions versus the backtracking. So you could imagine those search directions just from a geometrical standpoint, these are not orthogonal, where these are orthogonal. These are clearly not orthogonal. But the word conjugate gradient means this pictorially versus this. Okay. So steepest descent just looks at the residual, but has no idea that it's actually, this search direction is the same as this search direction, is the same as this search direction. It hasn't learned anything. Whereas CG is much more sophisticated. It's guaranteeing you don't go this particular path again. Okay. What's fascinating about the conjugate gradient method is that if you assumed exact arithmetic, no problems with a machine implementation with finite arithmetic, which we really do have, it turns out in theory that the conjugate gradient method actually will converge in at most no more than n steps for an n by n linear system. So if it's a 50 by 50 linear system, you're guaranteed in exact arithmetic that conjugate gradient would converge in 50 iterations. So the early designers of the method actually thought of this as a direct method, not as an iterative method, because it would actually guarantee your solution in n steps. But for practical applications and the way we tend to use it in scientific computing, we really don't want to go n steps. If it was 100,000 by 100,000 linear system, we really don't want to go 100,000 iterations. We'd like to stop much, much sooner than that, and we typically do. But I just wanted you to point that in theory, it acts like a direct method, that it's guaranteed to converge if the matrix is symmetric, positive, definite in steps. So now, given the constraint of conjugate directions from the pictorial sense to get faster convergence to the minimum of f, we can now explain exactly what that beta k parameter, the step size in the search direction, we have beta k at now, we can have beta k as well as sk. So since now we want our search directions to satisfy this kind of recursion, again, the actual solution xk has a recursion. In conjugate gradient, you have two recursions going on. You're trying to update a search direction as well as updating your guess to the solution, or the x that minimizes out. Well, for conjugate gradient, we require this relationship that sk transpose a, sk plus 1 transpose a sk, that must be 0. So then necessarily we must have this form, because we know what our sk plus 1 must look like. We just defined it. We substitute in here. If we solve for beta k, then this tells us exactly how to advance the search direction. Okay. Again, that's the numerator is a scalar and the denominator is a scalar. And again, because the matrix is symmetric, positive, definite, we're not going to have a 0 denominator down there, because sk transpose ask has got to be strictly positive. So you can see, again, the importance of that positive definiteness. So let's look at the algorithm, and then we'll look at how it's implemented in the book, and then I'm actually going to run an example with you so you get familiar with how you will use a method like this in code. And it's fairly straightforward. So the initialization of the method, just like Gauss-Seidel, you have to choose a guess at the solution. The more you know about the problem, the better. But you have to choose something. Then you immediately compute a residual, b minus ax0, because remember, we've got to have a search direction to improve upon. We're going to start with the residual. So the very first search direction for conjugate gradient is the same as the search direction for steepest descent. You have to start with something. So we're going to compute a residual, use it as the first search direction, and then improve upon it. The remainder steps of the algorithm is the main loop. Basically just going through this process of improving our guess at the minimization of f, which is our xk vector, and updating our search directions. So you can see in this loop, as defined here, from k equals 0, 1, 2, so forth and so on, the update of our step for our solution. And again, we already have started with the first residual for our search direction, so we know what sk is. So we can update our guess to the solution, and then we have to compute our new residual. So you compute your new residual, and again, in the process, if you solve the linear system really well, you're done. So if the residual is less than some very small tolerance value, and again, the user has the ability here to decide how accurate you want to be. That's probably one of the biggest differences between a dense method and an iterative method. The dense method is basically going to operate at full precision that you've defined in the data. You know, if you're running in 32-bit versus 64-bit, and how much memory you've allocated to the numerical values, that's pretty much what you're going to iterate. You're going to compute to. These methods are really nice if you have applications where you really only need a few decimal digit accuracy. And believe me, there are several where you don't really need 16 digits of accuracy. You only need an approximate solution. Gauss-Seidel and conjugate gradient are beautiful for those kinds of situations. And again, if you haven't solved the linear system well, or that residual isn't suitably small, then you need to continue on with the optimization problem and be able to update your search directions with computing beta k and then updating it, and then just continue with the loop until you finally get a residual that's small enough and you're happy with that particular estimate of the solution to ax equals b. One thing that you can really show just from the construction of the algorithm is that as you generate these residual vectors, r1, r2, r3, as indicated in this step right here, you can show that they're mutually orthogonal. And since that Ri transpose Rj equals 0 for I not equal to j. So what's really happening is those residuals are forming a basis for Rn. Now, playing upon what I just said in terms of the fact that the residuals are forming a basis, then if you have R1 through Rn, and you know that they are mutually orthogonal, and you're in Rn space, and you have produced n independent vectors that are mutually orthogonal, then you can automatically conclude that if you were to iterate one more time and produce, say, the n plus first residual, it would have to be 0. Why? Again, because R1 through Rn form a basis. So anything beyond Rn is got to be dependent upon, it's not independent from the others, because those n vectors form a basis for all of Rn. Okay. So again, this proves the absolute convergence of this method. It will converge in n steps because you're going to generate a basis for your space. But again, keep in mind, in practice, we would never do that, because if it's a huge problem, you really don't want to iterate to 100,000 steps just to know that the 100,000 plus one residual vector would be equal 0. But this is the upshot of it all. It means that conjugate gradient theoretically converges in steps, but typically we are looking at convergence to accuracies that are, useful for applications in physics and chemistry and other places, and much, much less than in iterations. So I'm going to show you the code as presented in the textbook. It's also available on Blackboard for you to use for testing, for homework, and study. And then I'll review an example of using it in 2.18 on page 97, as well as demonstrating the code running, the Python script running for that example. So on page 91 and 92 of the textbook is the definition is the expression of the conjugate gradient Python function, and I just wanted to go over a couple of points with it. Again, it uses NumPy because we're using arrays. The function is called conj grad for conjugate gradient. It's needing a function. They're calling it AV, and you can probably guess what that does, is you have to provide it a function to do the multiplication of your matrix A that defines your linear system times the vector. And then it's going to return a solution X. It needs the right-hand side B, and again, we need a very small tolerance for convergence purposes. In this case, it's defaulting to 10 minus 9, but the user can enter whatever they want in terms of the accuracy. So X is the guess at the solution. It has to start somewhere. Again, B is the right-hand side vector. And this particular function, there's no worry about it destroying B at all. All right, it's just going to update your initial guess X and return that. It's also going to return the number of iterations. So you can see down here at the very bottom, it's returning the guess solution, and I is the iterator parameter for that for loop, which we kind of illustrated in the pseudo algorithm earlier that was in the slides. So again, the nice thing about Python is this particular code looks just like the notes that we just had. Again, you don't need to ever pass the n as a parameter to Python functions because it can derive the lengths from your inputs. So we can get n from the length of b. We'll go ahead and compute a residual. So clearly the user has to be able to provide this function AV. Right? And in the doc string it says user must supply function AV of v that returns the vector a times v. And then the rest of it is just computing the alphas, for the update of the solution. We need the step size alpha with our search direction S. S, notice, is a copy of the residual, so we get separate memory and store that into S. So the first residual, which would be the same thing as doing the step of steepest descent, is an S, and then we update alpha, update our search, then take a residual, test if it's suitably small enough for us to say we've solved the linear system, else we'll update our search direction and continue on. Very elegant, very simple, and really, really a nice function to use for solving linear systems. Now the example problem in the textbook on page 97 that I wanted to go over with you, just make sure you understand how the code is being used and how a user would have to supply that multiplication function. This is example 2.18, which says, solve the previous problem we've seen in example 0.217 with the conjugate gradient method and use n equals to 20. So we're going to solve a 20 by 20 linear system. Just so we can review, since I have a bookmark on my electronic copy of the book, again, this was the problem with having 2's down the diagonal, -1 on the super diagonal, -1 on the subdiagonal, and then 2 1's on the corners here. And so it's a pentadiagonal system. It's 5 diagonals, and most of the elements are 0. And you can see the symmetry is clear, but it turns out this is also symmetric positive definite. It's also positive definite. Right. So if we go back to our example, right, the user must provide a function, and this type we're gonna call our function AX. And so if you look at how conjugate gradient is called here, we are passing it the name. You just simply create the function and pass its name. So Python will accept the name of the function as the entry point for using it within the conjugate gradient function that we defined earlier. So in this case, you just cater your matrix appropriately. Use the non-zero structure of your matrix to demonstrate how I'm supposed to get all the components of A times the vector V. And that's what you see here, it exploits the it shows you how you would get the first component, and then how you get 1 through n minus 1 components, and then how you would get the n minus 1, or the last component, because it involves the last row of the matrix. This is the first row, and this is all the interior rows. And so you can see the diagonal 2 there, and the super diagonal 1, minus 1 here, and then in this case you can see the negative 1 subdiagonal, the main diagonal 2, and then the super diagonal minus 1, and so forth. So that's what iterative methods do. You customize the matrix. You don't operate on the matrix itself. You simply want to know how it acts as an operator. In this case, how does it multiply times a vector? What does the product of it and some vector look like? And so we return AX appropriately here. And then the rest of it's pretty straightforward. In this linear system, this code, you let the user decide what the size of n is. We set b equal to all zeros except the last component equal to 1. So the last component will be 1. We take an initial guess of all zeros. That you could play with that. Choose it as a random guess. This is just initially 0. Doesn't matter for these purposes. We can maybe we'll play around with it just to see the difference if we choose a different starting value. But you can see it's just printing the solution after you call conjugate gradient, and then return the number of iterations. Again, it returns the guess at the solution, or hopefully an updated to the guess the solution, or hopefully the solution itself, or very close to it, and the number of iterations. Okay. And then the example they show you is how to run it with 20. If you were running it with equals 20, here's what the solution would look like, and it would converge in 90 iterations. And they do point out that if you were to do Gauss-Seidel, it would have taken 259 iterations. This is the reason we consider conjugate gradient to be much more efficient in terms of how it would converge to the linear system, solution of the linear system. So I'm showing you the example 2_18.py file that I also provided to you on Blackboard, just so you'd already have code that calls conjugate gradient and solves the problem from actually example 217, that pentadiagonal system. And again, this is just an illustration of defining the function to do the matrix times a vector, and then calling it like the book did, AX, and then passing it to conjugate gradient to use. So just wanted to illustrate that, if you were to run the code just as illustrated in the book, prompting for the size of the problem, they used 20, and you would get what they had in terms of what the solution is, 9. It's interesting to say, well, what if we tried to execute it again and changed it to, a much larger, let's say 30 equations versus 20? Well, it takes a little bit longer to converge. Converging to the 10 to the minus 9 tolerance, right? So that's consistent. The larger the problem, will take a little bit more iterations. We could go back to that example and say, well, notice that again, the default, oh, actually I should point out that it was running for a solution tolerance of 10 to the minus 2, which means it was, just asking for an approximate solution. That's not a very small value for the residual. If we go back and say, all right, let's make it a little bit much smaller problem, and then ran our code for it with 20 equations, that would still be 9. But if we ran it again and go to 30, perhaps it's still 14. So it's interesting that we're getting full accuracy, for these smaller problems, regardless of the size, which is good. But sometimes you might find it, that the number of iterations is too high, and you can back down this tolerance if you want. If that's too small, you could back it down like we had earlier. Here's something else. Again, we pointed out that the initial guess is all zeros. One thing we could try, just to see what the difference is what if we were to take it to be all ones? So we could change this function to ones. From NumPy, we would import ones as well as 0. Just out of curiosity, if we were to run the code and then again say 20 iterations, the solution for the most part is the same. The number of iterations is still 9, not much change. So for some problems, you might notice that changing the initial guess might matter, and sometimes it may not. And again, the more you know about your problem, the better. So you have the conjugate gradient module, you have the example 2.18 available to you, and again, the next quiz will be focused on just the iterative method component of this chapter, because we're ready to move on to interpolation and curve fitting in the next lecture.